Welcome back. I have a number of problems that we can go through together pertaining to the homework.
And hopefully, this will help a number of students out this week as I am still in Rapid City. So let's go through a couple of these together. All right. This particular lecture will be a continuation of the earlier lecture into rates, ratios, and formulas. So if you haven't watched that, go ahead, watch that first, and then feel free to skip ahead to this particular video after you are feeling confident about what you learn within that particular lecture video. Okay, so the first types of problems that we'll encounter in our homework are problems where we're given a ratio in statement format. And so there are a couple of different ways that you might be given a ratio style problem. And one of the ways that's very, very common on a standardized test would be to just give you a statement and ask the student to interpret what the ratio is supposed to look like as a fraction. And so you may be given a statement such as 32 inches to 6 inches and identify the corresponding fraction or the fraction that corresponds to the particular statement. And of course, on a standardized test, you might be given a number of different options that you can, uh, you know, presumably cancel out or rule out by process of elimination. But necessarily, you'll have to be able to interpret the ratio correctly. And another way that you might be given a ratio style problem is, of course, with using the ratio notation, which has a colon. So you may be given something like 32 inches, colon, 6 inches. And you're asked to interpret what fraction corresponds to the following ratio. All right, so all we have to know in order to complete these problems is that the numerator of the fraction that we're trying to identify is represented by the numbers that are to the left of the colon. So this 32 inches is in fact the numerator of our fraction, and the denominator of our fraction will be everything to the right of the colon. And so in this instance, we have 6 inches that is in our denominator. So we've got 32 inches on top, 6 inches on bottom. And by the way, guys, what you're looking for with ratios is the units need to be the same in the numerator and the denominator of your fractions. So in this instance, we have 32 inches on top, we have 6 inches on bottom. The numerator and denominator units are the same, so they cancel out, giving us 32 over 6, which we know can reduce by dividing by 2 on top and 2 on bottom, to 16 over 3, because 2 goes into 6 3 times and 2 goes into 62 16 times. At this point, you can do long division. Go ahead and divide 3 into 16. 16 goes into 3. I'm sorry, 3 goes into 16 rather, 5 times. 5 times 3 is 15. Subtract, you'll get 1. Go ahead and give yourself a decimal place and drop the 0. 3 goes into 10 3 times. 3 times 3 is 9. And subtract, and it appears to be the case that you will get a repeating sequence of tens that you can keep dividing 3 into. And so you should get 5.33333 continuing. So 16 over 3 is roughly equal to 15.3. I'm sorry, not 15, but 5.33.
Excellent. Now, of course, the last question would be, so what? How do we interpret what this answer
Actually means in the physical world. Well, if you recall from the first lesson, a ratio is otherwise known as a scaling factor, and it's a way that you can represent a drawing on paper that's either bigger than what you might be building in the real world, or what you might be trying to represent in the real world, or the drawing could be smaller than what you're trying to represent in the real world. And how that works is usually if the denominator is bigger than the numerator, you're saying that you're going to scale up the drawing from some initial amount to some final quantity. So if you had 1 to 100, it means that on your drawing, you have 1 unit for every 100 units in the real world. Okay. And vice versa. If your numerator is larger than the denominator, it means that you're scaling down. So in this instance, we have 5.333 or 16 over 3. It means that in our drawing, if we have a big triangle, for every 16 units of this triangle, there are exactly 3 units of the object that we're actually going to build in the real world. So if this was 16 units, then we would have 3 units for our real world object that we're trying to build, because again, it's 16 to 3 or 5.33333. So 5.33333 means that you've got roughly 5 units to every 1 unit. So remember, this 5.333 is the same thing as 5.333 over 1. So you could also say that you have roughly 5 units to every 1 unit in the real world, or more precisely, you have 5 1/3 unit to every 1 unit in the real world. So it doesn't really matter how you want to represent that particular object. Okay.
The next type of problem that you might encounter
Would be to a problem which asks you to construct a particular rate given a statement. So you might have a statement such as a train travels at a rate of 75 miles per hour, and we're trying to figure out how do we interpret the actual rate that's given to us in the problem statement? How do we represent that as a fraction, if you will? So in this instance, we're scanning through these problems and we're going to be looking for words like per, words like every, words like to, words like in, words like for each. Sorry, I don't know what's actually going on here. I don't know why my computer's doing that. That's a little weird. I wasn't expecting that. But yes, you're looking for every, you're looking for to, you're looking for in, you're looking for each. And if you see one of those words, one of those keywords, you're actually going to look to the left of the keyword, and that's going to be your numerator quantity. Here's my keyword. Then you're going to look to the right of the keyword, and that is going to be your denominator. So if we were to construct the rate, we would have a fraction set with 75 miles in the numerator and 1 hour in your denominator. Note, per hour means that the hour would indeed be the units in your denominator, but since nothing has been specified, we just write 1 unit. So 75 miles per 1 hour or per hour.
note that miles per hour can usually
Be abbreviated as mph, but if the problem statement is simply asking for a rate, then 75 miles over 1 hour is just fine. The only interesting thing about rates is that you're going to have some unit of measure that is potentially different than another unit of measure in your denominator to the numerator. So if you'll see in this example, we have 75 miles in our numerator, but the unit in our denominator is actually hours. That's a bit different than working with ratios where you actually have unitless quantity that is given here. So like the 5.333 over 1 is unitless. This isn't saying that we're measuring in inches. This isn't saying that we're measuring in feet. We don't even know if there's a measurement at all. This is a completely unitless quantity. Okay. All right, let's carry on. A recipe calls for 9 pounds of honey to 3 gallons of water. So let's go ahead and try this one. So 9 pounds of honey to 3 gallons. 9 pounds of honey. Two is my keyword. I look to the left of my keyword. I see 9 pounds, so I'm going to write that in my numerator. I look to the right of my keyword. I see 3 gallons. I'm going to write that in my denominator. And this is my answer. Now you'll note that 9 pounds to 3 gallons is going to be equivalent to, if we had simplified this fraction, 9 divided by 3 gives you 3. So we'd have 3 pounds to 1 gallon. And that's probably the best answer. All right. One more problem. A factory is able to produce 100 units in 17 hours. Well, here's my keyword, in. We're going to look to the left of my keyword. I've got 100 units. That's my numerator. And I look to the right of my keyword. Here's my denominator. Got 17 hours. And since 17 doesn't divide 100, this is the best I can do. I've got 100 units in 17 hours. All right. A salesman is able to sell $900,000 worth of products every 2 months. So there are a couple of different ways we can interpret this particular statement. However, every is going to be our keyword. We know 2 months would surely be in our denominator. So here's my 2 months. $900,000 could be in our numerator. And of course, 900 divided by 2 should give me $450,000 to 1 month. And this is going to be your best answer. All right, the third style of problem that you'll encounter on your homework are called unit conversion problems. For a unit conversion problem, you're going to have to go to your unit conversion chart, bust it out, and do a quick conversion. My apologies, the cuckoo clock decided that it was going to go off. It goes off every hour here in Rapid City, so it is what it is. All right, so suppose you've got 55 milligrams to grams. Well, 55 milligrams and I'm trying to convert it to grams. We need to bust out our unit conversion chart, and we need to figure out how many milligrams is in 1 gram. Well, it turns out that 1,000 milligrams is equal to 1 gram. So how you can interpret this particular statement, 1,000 milligrams is equal to 1 gram, is as follows. You may interpret this as being 1,000 mg over 1 gram, or we could interpret this as 1 gram to 1,000 mg. Now we have to select which one of these rates we're going to use as a conversion for converting 55 milligrams to grams. We want to convert 2 grams. We're converting 2 grams. Grams is the goal. So we want grams as a unit at the end of the day. Since I've done these types of problems before, I would probably pick the second option. So I'm going to go ahead and multiply 1 gram over 1,000. I'm not sure what's happening here. I don't know what's going on. So 1 gram to 1,000 mg. And when we multiply these two quantities together, what's going to happen is, well, 55 times 1 will happen in your numerator. You'll have 1,000 in your denominator. And then in terms of the units, you've got grams times milligrams over milligrams. And your milligrams are going to divide out, definitely giving you grams at the end of the day. So 55 times 1 is just 55. So we have 55 over 1,000. And 5 can definitely go into 120 times. So 5 should be able to go into 1,200 times. And 5 would go into 55 11 times. You've got 11 over 200. And by the way, note that this is going to be measured in grams.
Now, while a fraction is okay
for these unit conversion problems, you're usually going to want to actually be able to represent this using a decimal, since the measuring device itself will likely be in decimal units as opposed to measuring using some sort of a fraction scale. So you would have to then go to the side of your page somewhere and figure out how to convert, 11 over 200 into its corresponding, fraction. So you would have to do 200 into 11, if you will. And of course, 200 goes 0 times into 11. So give yourself another 0, and it would go 0 times into 110. So then you would have to guess how many times it goes into 1100, and 200 should be able to go to 5 times into 1000. So you'll get exactly 1000 with 100 left over. And you can do this again, drop your 0. 200 will go into 1000 another 5 times, and you'll get a remainder of 0. So this 11 over 200 grams should be equal to 0.055 Gs, or 55 grams, if I did my math correctly. No guarantees, so go ahead and double check that. But I believe my math is correct. All right, so for the last style of problems, I give you a equation, and you're asked to plug in numbers into the equation. So you may be given something like P is equal to 2L plus 2W, and you're given some numbers. So in the easiest case, your numbers are unitless, which is great. So in this instance, there are no units on my numbers. I don't have to keep track of units throughout the problem statement. If you're given units, you have to keep track of the units. Units are very important. Units tell you if you've got a correct answer or an incorrect answer. So you really need to pay attention to our units. In this instance, since 7 has no units, we'll just do 2 times 7, or 14, and 2 times 15 gives you 30. 14 plus 30 gives us 44. All right, guys, that's all I've got for you in this particular lesson. Take care.